Hello everyone and welcome to Sky Scholar. 2025 was an eventful year, but with fewer than anticipated video releases. Still, before we tackle today's topic, I have several pieces of exciting news. First, I have decided to post all of my astrophysics related papers on Substack. Here is the address. Anyone who is interested to join the Substack can do so for free. That would also enable direct messages to those who have supported my work these many years. Additionally, we have also decided to start reposting these YouTube videos on Rumble at this address. YouTube has been a fine method of communication, but it is time to utilize additional platforms. Secondly, Jim Keller has invited a group of individuals to San Francisco at the end of the month to discuss launching private satellites into space. These satellites will be designed to test a range of ideas, including some related to the microwave background and to the sun. I will try to include progress updates on Substack. We recognize that it may be several years before a satellite can be launched, but discussions are now underway. Finally, after much consideration, I have decided to write a textbook on condensed matter astrophysics. At this stage, many ideas exist only on YouTube and they need to be further developed in writing. If you join the Substack, you may get updates about that progress as well and receive an announcement when the work is finally completed. For today, however, I wish to turn my attention once again to metallic hydrogen, blackbody radiation, and the solar spectrum. You recall that I previously addressed the solar spectrum in these videos, and I also analyzed the spectrum in the context of the standard solar model in this paper. I have highlighted previously that the standard solar model utilizes a wide array of processes which have absolutely nothing to do with thermal radiation in order to account for the solar spectrum. This approach cannot be correct. I have also emphasized that whatever takes place in graphite on Earth must also take place in the Sun in order to properly account for the solar spectrum. As such, the only process which is available to account for this thermal radiation must rely on the vibration of atomic nuclei within the confines of a lattice. At this point, however, there is more to consider. That is because the solar spectrum is not perfectly Planckian. Specifically, it deviates from the pure blackbody profile in these regions. How can one account for these deviations in the context of a vibrational hexagonal planar lattice? For instance, the underlying cause of super-Planckian behavior in this region of the solar spectrum is never even addressed by the standard solar model. By the conclusion of this video, you will view the solar spectrum in a manner which was never previously considered. Since the photosphere of the Sun must be comprised of metallic hydrogen in hexagonal planar configuration, we begin by reviewing the hydrogen phase diagrams. Over the past few years, an ever-growing number of articles and reviews have appeared relative to such diagrams. For the sake of today's discussion, simply take notice of the region for molecular and metallic solids and how the curve comes down as densities increase in this region. Such behavior stems purely from calculations, as the associated densities have never been reached on Earth. Next, consider this hydrogen phase diagram presented by Seiichiro Ichimaru. The scales are the same as in the previous figure. The general position of the molecular solid and metallic solid region from the Berkeley figure we just examined can be superimposed. A dramatic discrepancy in the region believed to contain these solids is evident. This serves to highlight that the hydrogen phase diagram remains poorly understood. Much of what is displayed on such phase diagrams can be questioned. Relative to establishing the correct phase behavior for hydrogen, it has been said that a major challenge for experiments with matter at extreme densities, temperatures, and pressures in general, and dense hydrogen in particular, is given by accurate diagnostics. Indeed, very often, basic parameters such as density and temperature cannot be directly measured and have to be inferred from other observations and theories. It has also been argued that The phase diagram of hydrogen is surprisingly complex, and identification of phases and phase transitions or crossovers very sensitively depends on the analysis tools. Various experiments and simulation methods may lead to strongly differing predictions which require careful analysis. And again, the high-pressure phases of condensed hydrogen and the liquid-liquid phase transition is particularly complex with many competing possible orders. The simulation results presented in section 2b2 and summarized in the phase diagrams of figure 4 through 6 include extensive predictions that still await experimental tests. For instance, the densest material known to man is osmium, with a density of about 22.6 grams per centimeter cubed. This would occur at about this position on the phase diagram. As a result, everything to the right of this point is pure conjecture. It is unclear that any material can reach such densities, especially when one considers that the average density of the Sun remains a mere 1.4 grams per centimeter cubed, while Jupiter and Saturn have average densities of only 1.33 and 0.7 grams per centimeter cubed, respectively. Yet those who study dense hydrogen accept without question the extreme densities currently hypothesized for white dwarfs and neutron stars. For instance, have a look briefly at this figure, again by Ichimaru. Notice how he adopts, without critical analysis, the densities of magnetic white dwarfs. In reality, all these densities are subject to reconsideration. Ichimaru does define regions where the material will be paramagnetic. This implies that the electrons are randomly oriented relative to their spin. Conversely, in the ferromagnetic region, the electron spins share the same orientation. In any event, rather than let dense hydrogen science govern how we see astrophysics, the reverse is now occurring. Accepted densities in astrophysics govern how all scientists who study hydrogen, including Ichimaru, view dense hydrogen science. Yet, as can be seen in this figure, when deuterium is compressed, there is no indication that the ability to reach ever higher densities is possible. Note that with increased pressure, the maximal density of dense deuterium stays constant. The experimental line, as defined by the solid dots with error bars, is essentially vertical. There is no evidence whatsoever that the points will move to the upper right with increased pressure. This does not support in any way the idea that hydrogen can be compressed to enormous densities. Yet condensed matter physicists never question the validity that enormous densities can be reached in the white dwarf or the neutron stars. In reality, there is ample reason to believe that white dwarfs actually possess very ordinary densities and that their lowered emissivity is simply a product of altered hydrogen crystal structure, as we have seen in these videos. In my opinion, the conclusion of the astronomers should not be so easily accepted by the condensed matter physicists. Too much of astrophysics continues to be based on outdated ideas originating using ideal gas models at the beginning of the 20th century. This includes most notably the Standard Model of the Sun. This situation could be greatly improved if condensed matter physicists ceased adopting results from the standard solar model and rather considered the stars anew in order to ascertain what is actually taking place. They should permit observational results in the stars to guide their insight, rather than simply adopting results from the standard gaseous solar model. This is the approach I have adopted and will now apply to the hydrogen phase diagram. That being said, let us now return to Ichimaru's first figure. As I previously stated in this paper, Ichimaru views the solar core as having a density of 150 grams per centimeter cubed, exactly as predicted by the standard gaseous model of the Sun. He also assumes the same mass density of hydrogen within the solar core. Since the solar core in the standard model is comprised of about 77% hydrogen, and the rest of the core is made up of heavier elements, Ichimaru accepts a mass density for hydrogen of 56.2 grams per centimeter cubed and a temperature of 1.55 times 10 to the 7th Kelvin for the solar core. He invokes that this core is made of liquid metallic hydrogen with a body-centered cubic structure, as I had cited in my 40 lines of evidence paper. If you examine Ichimaru's figure, you will note that he places fluid metallic hydrogen in the interior of the Sun from a log of density of about minus 1.3 or 0.05 grams per centimeter cubed to the core. As a result, Ichimaru is now placing fluid metallic hydrogen in the lower convective zone of the Sun. Since he accepts all the densities established by the gaseous standard model of the Sun, he is unable to account for the solar spectrum using a hydrogen lattice. His Sun contains a classic two-component gaseous plasma at the level of the photosphere. This is because Ichimaru lacks the density required to have a hexagonal planar lattice at the surface. This is in very sharp contrast to the model I have proposed. Along these lines, once again, I cite the work of Chandrasekhar on rotating liquid masses. The mathematical treatment of such masses will end up being much more relevant to the stars than the current standard model, precisely because it appears that the Sun has a relatively uniform density. In this regard, given the densities required to enable the formation of a hexagonal planar hydrogen lattice on the solar surface, it would be reasonable to estimate that solar densities range from perhaps 0.7 grams per centimeter cubed at the level of the photosphere to about 2 grams per centimeter cubed at the core. In the end, Ichimaru sidesteps the fact that the average density of the Sun is only 1.4 grams per centimeter cubed, even though he recognizes that dense hydrogen will behave as condensed matter at very similar densities. He does not consider that the Sun could have a relatively uniform density throughout. In his review, Ichimaru treats only 3 lattices: the hexagonal closed-packed structure, the face-centered cubic, and the body-centered cubic. He does not address the hexagonal planar lattice for hydrogen, the structure which is central to the liquid metallic hydrogen model of the Sun proposed in my work. Rather, he simply mentions that in a supercooled one-component plasma without an external field, layered structures, that is, a one-dimensional order, develop first in an arbitrary direction. Interlayer, that is, two-dimensional ordering, then follows, which would favor formation of the face-centered cubic hexagonal closed-packed, that is, hexagonal local clusters. He does not consider an intermediate hexagonal planar lattice structure. In this regard, Neil Ashcroft, one of the world's preeminent theorists and experts in the hydrogen phase diagram, wrote to me upon publication of the 40 lines of evidence paper. At the time, he concurred relative to the importance of the hexagonal planar lattice for hydrogen and highlighted this paragraph from his work. On little reflection, it is apparent that all the qualitative remarks just presented on the band overlap state in dense hydrogen could also have been made with minor modifications about graphite, a tetravalent hexagonal band overlap 1 atmosphere semimetal. Accordingly, it is instructive to examine the known optical characteristics of graphite. In the visible range, graphite appears black. To some extent, these characteristics are reported to be shared by very dense hydrogen. One possible choice for the structure of dense hydrogen, consistent with hexagonal symmetry, is actually a graphite-like arrangement. Despite this conclusion by Ashcroft, Ichimaru neglected to allow for the existence of dense hydrogen at the surface of the Sun. As a result, he has remained unable to account for the creation of the solar spectrum, the central observation relative to our star. There is much more that can be said about Ichimaru's figure, and that will hopefully be left for another day. For now, we move to the hydrogen phase diagram presented within a comprehensive review published in 2024. The authors of this review represent a who's who in metallic hydrogen science. However, without exception, each of these authors accepts the densities associated with the standard gaseous model of the Sun and the stars. They never do the inverse, namely place the stars in the context of what might be reasonable for condensed matter physics. In this figure, the x-axis now represents pressure in gigapascals rather than density. Despite this change in axis, the general features remain the same as in Ichimaru's figure, as it is easy to convert the pressure scale to density. Once again, for instance, everything to the right of this line represents conjecture. Nothing in this region has ever been measured, as the most elevated pressures ever produced on Earth for hydrogen experiments are on the order of 500 gigapascals. The initials PPT and LLPT represent the plasma phase transition and the liquid-to-liquid phase transitions, both of which are of questionable existence and derive primarily from theory. The red dotted line delineates the region where solid atomic hydrogen is believed to exist. Classical TCP stands for the classical two-component plasma. For our purposes, the key region is the fluid hydrogen region, as its temperature range corresponds to the temperatures associated with the stars on the main sequence. In fact, it is the hypothetical PPT region that we wish to define, with the guidance of the main sequence stars, as we shall soon see. When condensed matter physicists utilize the term liquid metallic hydrogen or fluid H region, they refer to a material wherein the nuclei occupy vibrational lattice points of a lattice and are free to move from lattice point to lattice point. This is not the same as a classical two-component plasma. In liquid metallic hydrogen, the electrons are delocalized, but the conduction band is somewhat restricted due to electron-lattice interactions, including interactions with lattice holes. For instance, Ichimaru speaks of itinerant electrons within liquid metallic hydrogen. As a result, such materials are not maximally conductive since the electrons are not yet fully delocalized. Next, let's focus on this region of the hydrogen phase diagram. This is an extremely important region for us, and it has been expanded in this figure. We begin with region 1, which represents a region of solid molecular hydrogen in hexagonal close-packed arrangement, as was confirmed by X-ray spectroscopy. Region 2 represents a similar structure but with broken symmetry where the hydrogen molecules are orientally ordered. Next, we come to region 3, which is still molecular in nature, but now the lattice is either C2/C-24 or CMCA-12 as illustrated here. If you examine the arrangement of the hydrogen molecules in these two figures, you will immediately notice that they are beginning to adopt a hexagonal planar arrangement. To the right of region 3, in blue, we find the semi-metallic solid state, and in red, the fully metallic state. In the dark red region, a fully reflective sample was measured, indicating the presence of a true metal. No information is available about metallization above 100 K for the region immediately above the blue and red regions. Not much is known about metallization in phase 4 and phase 4 prime. These phases are still molecular in nature. They are thought to be comprised of molecular layers intercalated with planar layers where molecules form almost regular hexagons. One can immediately notice that this is an evolution of structures proposed in region 3. In phase 5, the structures are not known, but the molecular bonds are thought to be weakening. Now, what is important for us is that when temperatures are increased, and as we move from structures proposed in region 3 to region 4, we are moving increasingly to the formation of hexagons. As we keep increasing temperature, we should now complete the formation of hexagonal planes and finally reach the hexagonal planar structure I have proposed for the surface of the Sun. Again, it is the region depicted by this arrow on the phase diagram which concerns us. What happens when temperatures are increased without a significant change in density? In fact, Ichimaru speaks precisely of this region when he writes, "Analogous process of metallization may take place when temperature is raised above the atomic or molecular binding energies of electrons. It is thermal ionization." In this video, I had discussed that in addition to pressure, metallization can be facilitated by increasing temperatures, as this permits electrons to jump into the conduction band. This is precisely the mechanism which is invoked by the arrow. The argument is that extreme densities do not exist. Rather, stars simply differ in the lattice they display. The selection of a lattice type depends on both pressure and temperature, including past physical history. This is reminiscent of graphite versus diamond. The two can exist under standard temperature and pressures, but they had very different physical histories, with diamonds previously subjected to extreme pressures. As a result, when we consider the stars, it is not only pressure and temperature which determines lattice structure, but the life history of the star. For instance, was it previously subjected to extreme pressure changes? Now, let us turn briefly to blackbody radiation in order to refine our analysis. If one considers the ideal blackbody spectrum, it is clear that it should result from an ideal lattice, namely the hexagonal planar lattice best represented on Earth by graphite. As a refresher, this is a structure of graphite, a lattice without defect, composed of hexagon with great 2D extent. Planes are then stacked together, adopting an AB-AB arrangement, such that in every other layer, the carbon nuclei are placed at the center of the hexagons above and below. This arrangement is the best example of a naturally occurring high-temperature blackbody on Earth. That is an important observation. If you want a nearly perfect spectrum, you must have a nearly perfect lattice. Notice how a graphite structure could be present in hydrogen as temperatures are raised above region 4. Remember that in region 4, molecular hydrogen still exists, but the hexagons are being formed. If one raises the temperature above region 4, then the dense hydrogen should become fully atomic and the hexagonal planar lattice should eventually be adopted. In fact, this was anticipated by Wigner and Huntington in 1935 when they first proposed the existence of metallic hydrogen. They argued that the hexagonal planar lattice would take less energy to form and might therefore be found first. Still, Wigner and Huntington did not address temperature ionization in their paper. Before we proceed, I wish to emphasize once again that when we deal with thermal or blackbody spectra, we are sampling the vibrational state of a system. As a result, we can only speak of apparent temperatures if convection and conduction are present, as is known to happen on the surfaces of stars. Remember that an entire lattice can move and carry a lot of energy in doing so. In fact, this is what happens when we have convection currents. I have previously addressed energy partition in stars in this video. That being said, we return to the solar spectrum. This figure represents the latest version of this spectrum. It displays the solar spectrum in red acquired beyond the Earth's atmosphere, then in blue at sea level, and finally displays the effect of atmospheric absorption lines in the final result. Let us concentrate only on the spectrum acquired above the Earth's atmosphere. For now, we wish to superimpose ideal blackbody curves on this spectrum, and we select those corresponding to 5,777 Kelvin, 5,900 Kelvin, and 6,000 Kelvin. When we examine this figure, we immediately recognize that the lattice which exists on the solar surface cannot be perfect. It must possess some defects, because none of these superimposed blackbody curves fit the solar spectrum perfectly. As such, we now consider 4 regions in this spectrum. First, the low-frequency region seems to follow the blackbody spectrum fairly well. Second, consider the region between the Wien's peak and the low-frequency region. Here we see that at 6,000 Kelvin, the solar spectrum does not produce enough emission to match the blackbody curve. In region 3, where the Wien's peak can be found, we note that the emission is actually super Planckian for all blackbody fits. On first examination, this would seem to represent a violation of the laws of emission, as many believe that nothing can emit above the Planckian maximum. So one has to ponder what possible mechanism could cause the sun to emit in a super Planckian manner over this narrow range. Finally, we come to the highest frequency region, region 4. Here we observe a breakdown of the blackbody spectrum. But why? Obviously, some of the loss of signal can arise from absorption by atomic species in the region above the photosphere, producing the Fraunhofer lines, but more can be considered. The accepted temperature of the solar photosphere is about 5,800 Kelvin. However, that value appears slightly too low, as it results in extensive superplankton behavior at the Wien's peak. That is to say that the solar spectrum has a much stronger emission in this region than predicted by a 5,800 Kelvin blackbody. For the sake of this discussion, we will focus on this curve, which superimposes a 6,000 Kelvin blackbody spectrum. This will allow us to analyze the principal aspects of the solar spectrum. Details advanced can then be simply modified to accommodate the small deviations which arise when other blackbody temperatures are used to fit the spectrum. To help us understand all these features, we turn to the structure of soot on Earth. Relative to its carbon framework and ignoring functional groups such as hydroxide, which are often present, soot greatly resembles graphite, with the notable exception that within soot, some carbon atoms are missing within the extended lattice. In essence, we are dealing with a somewhat broken graphite lattice. It is also important to note that unlike graphite, soot cannot be used to build high-temperature blackbodies because the soot lattice breaks down at high temperature. Soot is often described as a fragile aggregate of nanoparticles. It can be used to generate excellent low-temperature blackbodies, but is unsuitable for elevated temperatures. Next, the imperfect structure of soot is adopted, and such a structure is imposed on the hydrogen lattice for the solar spectrum. We ignored the delocalized electrons, and only the protons are depicted in hexagonal planar arrangement. Allowance is made for the presence of some lattice holes where no nuclei are present. At the same time, we note that in a liquid metal, nuclei are able to move from one lattice point to another. We begin with the low-frequency region, which properly follows the perfect blackbody spectrum. At these frequencies, insufficient energy of vibration is present to cause any nuclei to move between the lattice points, as we note no distortions in the spectrum other than those caused by absorption of atomic and molecular species above the solar photosphere. While the overall lattice is imperfect, the scale of the lattice defects are small relative to the wavelengths of the low-frequency oscillations. Insufficient energy is present in this region to cause displacement of protons into lattice holes. As a result, everything appears just like it would in graphite. Next, we move to the intermediate region 2. In this region, a drop in emission is noted relative to an ideal blackbody at 6,000 Kelvin. This tells us that the lattice defects are such that now certain lattice vibrations are reduced in number. There are two possible explanations for this reduced emission. First, the lattice defects could be on the order of the wavelengths of the lattice vibrations in this region of the spectrum. The loss of a certain percentage of vibrations as a result of lattice defects could account for decreased irradiance in this region of the spectrum. Secondly, should an atom move into a lattice hole, any excess translational energy in displacement could be added to an existing vibration, resulting in emission at higher frequencies. Mathematically, this could be expressed in this manner. This could help to account for the increased emission in region 3. The increased emission in region 3 might also be explained by considering region 4. In region 4, the energy contained within the lattice vibrations is now very high. Consequently, the lattice is too weak to support these vibrations without the displacement of nuclei. As a result, the energy of vibration gets divided into two parts. Some of the energy is used to push a nucleus into a lattice hole at a new lattice point, and the remainder is emitted at a lower frequency. This accounts for the superplankton emission at the Wien's peak. Mathematically, one can think about it this way. The initial vibrational energy in region 4 is now equal to the energy lost in the translation of the nucleus into a lattice hole, plus the energy emitted at a lower frequency. Some of this energy is emitted at the Wien's peak, but of course, some could also be emitted within a lower frequency within region 4. For instance, in this area. As a result of such processes, the appearance of the solar spectrum could be qualitatively explained. In this analysis, advantage has been taken of the lattice itself to account for the solar spectrum. This is in keeping with the realization that on Earth, within a compound such as graphite, the only means of generating a blackbody spectrum must arise from the vibrational lattice itself. No other options exist. As a consequence, the real situation in the laboratory is completely unlike what has been advanced by proponents of the standard gaseous solar model to account for thermal emission in the stars, as I have previously discussed in this paper. Current astrophysics invents a group of processes which have absolutely nothing to do with thermal emission and mix an extremely wide array of processes in an attempt to account for the solar spectrum. Such an approach is contrary to spectroscopic principles. As I have stated in the past, it takes a thermal process to produce a thermal spectrum, not a set of unrelated processes, none of which can occur in graphite and none of which contribute to blackbody emission on Earth. Now that the solar spectrum has been discussed by invoking imperfections in the lattice and movement of nuclei into lattice holes, what about the other stars of the main sequence? As I have previously mentioned in this video, stars on the main sequence must also possess a hexagonal planar lattice. Here is a figure displaying a series of spectra for main sequence stars. Each spectrum includes both the blackbody spectral shape produced by the stellar photosphere and the absorption lines produced by atoms above the solar surface. For the O, B, and A-class stars at the top of the figure, the spectra appear to closely match that of a theoretical blackbody with little distortion. Of course, individual stars may differ from these examples, but as a rule, one would expect that the hydrogen lattice in these three cases should adopt a nearly perfect structure, much like graphite. This tells us that as the apparent temperature is increased on the hydrogen phase diagram, the lattice becomes more organized and adopts a configuration much more like graphite, which allows it to deal with the higher vibrational energies. The Sun itself is a G-class star, and we have just described this spectrum in detail. Lower temperature stars should have even less well-formed lattices than the Sun. This occurs as a consequence of their lower apparent temperatures, resulting in lattices with more holes and imperfections. In stars of lower temperatures, there is also an increased presence of molecules and non-hydrogen atoms, which can act to further disrupt the hexagonal planar lattice. It is clear that a proper understanding of the solar spectrum can only come from the careful consideration of lattice structure by computational physical chemists. This, in turn, mandates a complete reevaluation of the hydrogen phase diagram. One thing appears clear: with increased apparent temperatures, the spectrum which we observe appears to be increasingly able to deal with lattice vibrations with little translation of atomic nuclei. It is only at lower apparent temperatures, when the lattice contains more holes and defects, that the stars cannot perfectly sustain the blackbody spectrum. This observation is in keeping with the hydrogen phase diagram and movement from the atomic fluid phase to phase 4 and the less ordered phase 3. In this respect, lower apparent stellar temperatures bring the stars closer to phase 4 from the atomic fluid phase and allows for more defects in lattice structure. Conversely, as apparent temperatures increase, the lattice becomes more rigid, enabling it to deal with stronger vibrations without atomic translation. As a result, lattices which exist at higher apparent temperatures should be closer to the perfect hexagonal planar arrangement, until eventually the temperature becomes so great that no lattice can withstand the vibrational energies involved. This helps us to understand why Wolf-Rayet stars are essentially devoid of a continuous spectrum and cannot be placed on the HR diagram. In summary, the solar spectrum is best explained by carefully considering the hydrogen phase diagram and by invoking an imperfect hexagonal planar lattice at the level of the photosphere. The displacement of nuclei into lattice holes can then be used to readily account for distortions in the solar spectrum, including the super-Planckian behavior at the Wiens peak. As previously stated, the stars on the main sequence all share the hexagonal planar lattice of the Sun at the level of their photosphere. They differ only in the extent of point defects in their lattice. Main sequence stars are cooling as they move during their life cycle down the sequence from O-class stars down to K and M classes. As for the Wolf-Rayet stars, when they begin to cool, they shall also enter the main sequence as O-class stars and begin their movement down the sequence. Well, that is all for today. If you enjoyed the video, promote the channel, mention the videos to your friends and to your local astronomy club. Support me with a like and subscribe for more videos as we look more closely at the sun, the stars, and beyond. Comments are always welcome down below, and I'll see you soon on the next video.